So the next stage is to go ahead and actually build the block design, which we do the switch block underscore design. Okay then. So again, this brings up the Vivado graphical environment, and we'll start editing the block design and putting in the logic, the signal processing to perform the software-defined radio function. So that will load up. Now it's running the tickle command blockdesign.tcl, which we'd edited from the pulse generator design, so it should have most of the bits that we need. In particular the Zynq block itself, some AXI interconnect. This is a clock converter, so it takes the data from the ADC clock rates and converts it up to the Zynq processor clock frequency, and that's where we're going to stream some data through into a FIFO. And this is the control registers, so if we have a look at these here, we should see, yes indeed, we've got the receive frequency and the volume which we're going to use to configure our radio, and we can feed back into here the measure of the signal strength. So we're going to plop in here our radio design. The other thing we need is the signal from the ADCs themselves. If we have a look at this block here, this shows the data being streamed out from the ADCs at the ADC clock frequency, and we can stream data back in again to fire up the DAC outputs, and we're going to send the speaker output to one of these, again clocked at the same frequency, this clock here. So one of the first things we do is for a radio design is use a mixer. The front end is conventionally a mixer, which is a multiplier, so we'll go into add IP and we'll look for multiplier. So let's have a look at this guy. It's got two inputs which we're going to multiply together to give the output, the mixed output, and then after that we're going to send that into a low pass filter. But let's configure the multiplier to start with. We'll be taking the signal from the ADC on 1 and some kind of local oscillator coming in on the other input. So we need to configure these. Let's configure them manually to make sure we get what we want. So these values are assigned values for the local oscillator and the signal. Now the input signal is a 14-bit value, the ADC is a 14-bit ADC. We could use 18 bits, but I think 16 will be sufficient. We're going to derive that from a block RAM that we're going to cycle through to generate the sine wave. Okay, so that's all good. So the input to the multiplier from the ADC and the local oscillator are going to be clocked at 125 megahertz. That's the sample rate of the ADC, and that's the clock we'll feed in here from the ADC clock. So the data comes out at 125 megasamples a second, so we're going to put after that a low pass filter. Now we want to get this down to audio rate, so it's quite a large decimation factor, and it's good to do that in two stages. So what we'll do is start with a CIC filter to do the first step, a big decimation step, and follow that up with an FIR filter to tidy up the response and get a nice tidy low pass filter down at the sample rate we need without using a huge number of coefficients that we would need to do if we wanted to do this in a single FIR filter. So let's pull up the CIC filter, CIC compiler. Okay, let's go for that. Now, IP integrator does like sticking blocks in random places, but we'll stick it just afterwards. We'll configure this. Now this is going to be a decimation filter. I'm going to take the sample rate down. Yep, we'll do that in 3 stages. That's good. And we'll have a decimate by 651, and that will get us down from the 125 megasamples a second coming in to 192 kilohertz coming out, which is a more standard audio sample rate, and then in the second filter we'll take that down to 32 kilohertz. So our input sample frequency is 125 units megahertz, good, and the clock frequency is also 125 megahertz, that's good. And the implementation options, well, let's take input data at 16 bits. We've got more than that out from the multiplier, so we'll just select what we think is where the useful dynamic range is, rather than treating too many bits. And we'll go for, again, limiting the output data width to 32. We'll use DSP 48s because they're cool. And let's just have a look at the summary. So that all looks good. Decimate by 651, 125 megahertz, and that all looks good. 15 clock cycles of latency, that's okay. Right, so we need to slice down the data width from 30 bits coming out of the mixer down to 16 bits going into the CIC compiler. Now this is going to be running at the full rate, so we're going to hold T-valid continuously high by connecting its T-ready, and we're going to stick a slice block between the two. Let's drag this in now to get it where we want. Shift this over, and we're actually going to take 30 bits coming in, and data out, let's just go from 28 down to 13, because in fact the multiplier went from 29 down to 0, that if you take 2 signed numbers, that 29th bit, bit 29, the top bit actually isn't going to do anything. That's just going to be a sign extension. That's 29 bits is sufficient to hold the output of that multiplier, so let's take it from 28 down to 13, and that gives us a data out width of 16. Okay. We'll put that into the data input, and we'll take the data from the multiplier, and as I say, the T-valid is going to be held continuously high because every clock cycle the data is going to be valid for the input, but it's going to be decimated significantly at the output, so we're going to need to use T-valid at the output of this block. The next stage is to put in the FIR filter to complete the low pass filter. So let's pull up an FIR block, FIR compiler, plug that here, get rid of that. And let's configure this. So, yep, we're going to enter the coefficients here. This is just some random filter, it's not the filter we want. We're going to enter the coefficients here. It's going to be a decimation filter, and we're going to decimate by a factor of 6 to get down from 192 kHz to 32 kHz. And so looking at the channel specification, we said we've got an input sample rate of 192 kHz, the clock frequency is 125 MHz, and okay, that's good. So we're getting 651 clocks per input sample, and overall by the end 3906. So that's our total decimation rate, and this looks good, except let's just change this. And output at 32 bits. Oh, set the input width to 32 as well. That should be good. Yep, it is. It's happy now. Okay. And we can simply connect up the AXI bus, so that automatically connects in T-data and the T-valid files. We don't need to wire them up individually. One thing forgot was to set the coefficients, so that's these here. We don't want those, we're wanting to set those to the filter that we want. Now, a good way of designing filters is to use one of the online FIR coefficient calculators. So one particular online resource for designing filters is this one, tfilterengineerjs.com. So we just need to enter in our design parameters. So it's 192 kHz sample rate. We're going to have a low pass filter to allow us to listen to AM radio stations. We're not looking for hi-fi, so let's just do something very simple, but you can play around with this. Let's go for an 8 kHz bandwidth, and we'll ask it to cut off, let's say at around 15 kHz, all the way up to the Nyquist frequency, which 192 kHz sample rate is 96 kHz, and design the filter. So, as I say, you can play around with this to get whatever attenuation you want, and whatever flatness performance you want in the passband and width, but the main purpose of this is to take out the lobes that we'll have generated with the CIC filter. So, here are the coefficients here. Now we've chosen int here, so we've got integer values. So we're going to copy these into the Vivado window. So copy. But to get them in here we need to separate them by commas. So let's just edit those values that we've got. Pull up an editor, paste them into here, and we want to get these commas separated, so we'll just do a search and replace for the, this is Linux, right? So we've got line feeds, we're going to replace with comma space, let's say, replace all, close, good. And so let's copy that again, copy and stick in here. Cool. Now it's complaining at the moment. If we just hit enter, yep, now it's happy. It's got our coefficient vector. So that looks, so yep, looks good. Fine. Okie dokie. Yep, systolic multiply accumulate. Fine. Okay, let's go for that. And now we're going to link all these blocks together to call that the mixer low pass filter stage. Now let's expand this window a little bit so it's not so cramped. So we select this, hold control, and these 4 items we're going to call hierarchy, which we'll call mixer and local oscillator. No, sorry, mixer and low pass filter. We'll call that. Okay. So that's given us a little block. It's not got any inputs and outputs yet, so let's make these pins. We'll call that sample clock. This one, right, whoops, no, right click the block, right click the pin, create pin. We'll call this one signal. So this is coming from the antenna, of course signal isn't allowed. Let's call input. So this is coming from the ADC. Another pin, and this is going to be local oscillator. That's a 16-bit value. The other one's a 14-bit value. That looks good. And let's pop this out again. And we're going to connect these clocks together. Everything's going to be clocked at 125 megahertz, the sample clock rate, and we're going to get the data out here. Pin. Let's call this let's call it demodulated signal. Okay. And we're also going to need this, which is going to be the strobe pin. Well, let's call it T-valid. This is going to produce pulses at about 32 kilohertz to give the rate of this signal. This signal is going to update at a 32 kilohertz rate. Okay, that's good. Let's close that. And we need to find the diagram. Okay, here we go. And that's our block now. So let's zoom out. The ADC clock, I believe, is one of these. It's this one here, ADC clock. So the sample clock will connect down onto that ADC clock. Okay. Nope, wrong one. What I meant to do was connect sample clock, right click, make connection, the ADC clock. There we go. And so that should now connect to that net, which is picking up the ADC clock. Okay, cool. So now we need the antenna input, which, as I said, we would pick up from the ADC itself. ADC, up we go. To antenna input. And the local oscillator, that we're going to have to create a local oscillator. So the next thing we need now is an input to the local oscillator here. But before we go ahead and do that, we just have a think about what we're doing here. So we're taking in a signal, demodulating it by beating it with the local oscillator. But if the local oscillator isn't exactly in phase and exactly the same frequency as the carrier frequency of the transmitter, we're going to see a bit of warble or variation on this signal here. So since we're wanting to build an AM receiver, what we'd better do is actually beat with the local oscillator at two different phases 90 degrees apart, and then construct the amplitude by determining that from the in phase and quadrature signal of the antenna input. So we'll actually need to drive two instances of the mixer and low pass filter with a local oscillator at two different phases 90 degrees apart. So firstly that means we need a second instance of this, so we'll copy it, Control C and then Control V to paste. Okay, now again IP integrator sticks that second copy at a random location, so let's zoom out, find where it is. Here it is. Okay. Also, let's rename these to be what we want. This one, let's go back into the main window. We'll call this LPF_I. So this is the I component of the signal, and this one we'll call _Q, the Q component of the signal. Okay, zoom in, and so the sample clock connect together, the antenna input connect together, but we'll put in, no, that's not what we wanted, connect to this, okay, and we'll send two different local oscillators 90 degrees apart to these two inputs here. So that's the next thing, is to build the local oscillator. So let's come out here again, zoom out, and let's build down here our local oscillator with two outputs. So what we're going to do is use a dual port RAM block. Now let's find it. Now we don't need to write this RAM block from the ARM processor, so this can just be a simple standalone memory. It's going to be dual port. We'll make it dual port ROM because we're going to predefine the memory contents to be a single period of a sine wave. So the port options, we will have the input width of, the output width of the data 16 bits. We'll make it 2048 values deep. That should give us sufficient resolution on that local oscillator sine wave. And we're going to use port B to send out the quadrature version of the local oscillator. So port A will be the in phase, port B will be the out of phase local oscillator. So what we're doing now is building DDS, a digital synthesizer. So the thing is to define the contents. We'll say we will load a file, and this is going to be a predefined COE file containing the contents of the memory, which is going to define this one period sine wave. Now you can either create this file yourself using Python or something, but we'll just recover a copy that was made earlier. And if you look at the presentation referred to at the beginning of this video, there's a link at the end of that presentation where it gives a repository where you can recover a copy of this file. But just for the moment, we're going to pick up this file here, a COE file. We can have a look at it in a text editor. So this is the sort of format you will see. These are the values, actually in binary here, that will be loaded into that block ROM. So we'll copy that over, copy, into the directory where we're going to be working. Okay, and then we'll just pick it up here. Browse str sinewave.coe. Okay, fine. Also, as is always good practice, from time to time it's a good idea to save this, just in case anything goes horribly wrong. And this is just saving in a block design format, but when we finish, what we're going to do is then export the design, so might as well go ahead and do this now. Export the block design as a TCL file and replace that block design TCL file that we used earlier to create our skeleton project. So let's find where that's going to be. Again, that's going to be instruments.str. In fact, it's this guy here. Okay, so we'll overwrite that with our newly developed block design. We're going to overwrite it. Yeah, I really do. Okay, so we carry on now. Here's our block ROM, and we need to drive this with a triangular wave, a ramp waveform, which is going to step through all the locations of this sine wave. So to do that, we're going to use an accumulator. So we will parameterize this now. We will drive it with a 32-bit value, which we're going to get from the control registers, the set frequency register value. So bring that 32 out, and it's going to mean adding accumulator. And so the input value we will take from this receive frequency here. But let's just carry on and finish off this, this local oscillator, because we want to drive this memory with two address inputs offset by a quarter period. So firstly we need to slice off the top 11 bits, 11 bits being required for the address bus of the memory. So we're taking oops, that's the wrong thing. Oh, here it is, this is the slice. Okay, so we're taking a 32-bit value in, we want to slice off the top 11 bits. No. Get this right, yep. So this goes to here, and the input goes. Well, we won't send it in directly yet. because we want to take two versions of this offset by a quarter of a period. So what we're going to do is do an addition. We need an add sub block. This we're going to make it a positive value unsigned. It's an 11-bit value. We want to add and create an 11-bit output value, and we want a constant input, and the value to give a quarter period offset will be this value. You can check that's correct. On here. Okay. Yep, everything's happy now. Okay, and so that these values arrive at the same time, because this will have a latency of 1, we'll just put in a delay block, and this is actually one of our custom made blocks which has been brought in by the config.yml file. That gives us just a simple 1 clock delay. Now our clock, of course, we'll bring in later. Let's just zoom in a bit here, see what's going on. So this value is going to come into the add sub, and let's tidy up the layout a bit. So we will regenerate layout. This is our delay block. Where's our memory? That's there. Okay, zoom in down here. So this will go to one address. This will go to the other. And this takes this ramp value, and so this is the ramp value directly, and this is the ramp value offset by a quarter period. Let's not bother with the clock enable, we don't really need that, so this will just go continuously. Now this whole lot here, control select, select, this is going to be an entity, and we'll call this local oscillator. Okay, and now it's jumped off somewhere else, so there it is. Okay, let's bring it back down here and have a look. Pull it out. So this is going to be our sample clock, and we're going to use the same clock everywhere. Okie dokie. This is our input value. So we'll call that set frequency. So that's what's going to be used to define the ramp rate of our address generator. So that controls essentially the frequency of our digital synthesizer. And the two outputs are going to be here. This is actually the offset one, so we'll call this Q, local oscillator Q. And this one here is going to be the local oscillator in phase component. Okay, we better enable the ROM chip. So we've got a constant value. It's just going to be a 1-bit width, a 1-bit value with a constant value of 1, and we're going to use that to enable the memory chip. Okay, let's close that. Don't need that for the moment. There's our block design here. So now we'll see our local oscillator. These are our two mixers, and we can now feed the local oscillators to the two inputs. Sample clock we connect to the ADC clock. Set frequency we connect to the value from the control we're going to set from the processor. Tidy up a bit. Okay. So now we have here and here the I and Q amplitudes of our antenna signal at the frequency defined by the local oscillator. So one thing that would be useful to do now is to define a signal level monitor which monitors the level of the signal at this point here, either here or here. The level will be the same. So we will try and average this signal and determine a signal level. So to average we'll use an accumulator. Bring this in. We're going to use an input width of 16. We're going to accumulate over quite a few pulses of order 2 to the 16 to get a 32-bit output. We're going to work in add subtract, so we're going to add the positive values and subtract the negative values so that we're accumulating the absolute value of the signal. Okay, and so what we'll do is slice off a little bit the top 16 bits of the signal, because from here we've got a 32-bit value, and we're going to take off the top 16 bits and put into our accumulator. Now, depending on whether this is positive or negative, we're going to add or subtract. And we know whether it's positive or negative by looking at the very top bit. So I'll copy a slice block. Oops. Look here. This is going to look at the top bit. And if it's a 1, it's going to be negative, and so we want to subtract. And that means not add, so we better put an inverter. So if you look under logic, and this will make it a NOT gate. We only need 1 bit. Okay, and we'll use that to control add bypass. Now we don't need that, so let's say no thank you. Okie dokie. And what else do we need? So this is going to accumulate a value, and we're going to every so often register the output of this and then reset this. So what we will need on this then is a clear, so that we can clear the accumulator and start adding up again, and then we'll need to register the value. So let's put in a register. Now this is again one of our custom blocks. That we can configure. It's going to be a 32-bit value, and we want to trigger that every now and again. So to do that we're going to have a counter. Let's make this a 16-bit counter. That's good. That should be fine. And what we'll do is just look at the top. Can we move this? No. Okay. Let's zoom out a bit. But what we'll need to do is we'll take the top bit of this, zoom out, yeah. Yes. We're going to take the top bit. This is a 16-bit value, and we're going to take bit 15, and when that goes high, which is every 2 to the 16 clock pulses, we will reset everything. And so we want to do that with a single clock cycle pulse, so that's our 1 clock pulse device. So that we'll use to trigger, and this we'll use to enable the register and also to clear the accumulator. So we'll connect up to the register and we'll have the output here. Oh, no, that's wrong. Delete that. That should have gone to the input. Okay. So zoom out a little bit more. So this right here we're going to put into a subsystem. So create a hierarchy, and we'll call that signal level detect. Okey-dokey. No inputs or outputs yet. That we'll put a pin which was our sample clock. Okay. And this here, the output of the register. Hang on. Let's move out. Work on this. This is going to be our output pin, and we'll call that signal level. This is our input signal. Yeah, why not? And that's the sine bit. The clock we're going to connect up to here. It's all the same clock. And that should now give us a signal level in 31 bits. So park that again. Go out to top level design. Zoom out. Let's move this in somewhere. So sample clock comes from here. Signal comes from here. This is our signal level out, which we're going to send back into the signal strength status value there. Okie dokie, so good. So far so good. So again we have our I and Q amplitudes. So the next thing now is to determine the overall amplitude taken from the I and Q components of the amplitude. So what we'll need to do is take the square root of the sum of the squares of these, and that conveniently we can do with something called a chordic block. So let's pull up the chordic. This is a very handy device in digital signal processing. Basically it does a Cartesian to polar conversion So we put in I and Q amplitudes and get out amplitude and phase. So we'll need to configure this. So we need to set up the functional selection, the various possibilities for this codec core. What a codec does is takes in complex input, or if you like IQ input, and by a series of rotations rotates that onto the real axis so that it's a purely in-phase component to determine the amplitude. And so in fact the version we want then is translate, parallel, yes, maximum, radians. This just is the format of the phase out. We're not actually going to use the phase, but we'll put into scaled radians because that's easiest, rather than getting phase in units of pi, then just have it a simple digital value. But for the amplitude modulation case, we just need the amplitude output. Okay, 16 bits, 16 bits, yes, this is fine. Scale compensation, that the amplitude actually ends up with the codec being 1.7, well, around about 1.7 times greater than the square root of the sum of the squares. And so there's this constant multiplicative error, but for doing AM we don't really care about that, so we don't waste resources recompensating the scale, so we'll leave that. So that's okay. The next thing to understand is how the data comes into this device. So it has 32-bit inputs and 32-bit outputs. The input actually has the I and Q amplitudes concatenated together as 16-bit values, and similarly the output concatenates the amplitude and phase, and in fact the amplitude is in the lower 16 bits. So we need to take these two components, the I and the Q, and concatenate them together. They're coming out as 32-bit values, so we better slice those back down to 16 bits. So, hey, I don't know which 16 bits to take. We've got this huge dynamic range of the input coming out of these demodulators, and depending on the signal level from the antenna, our useful data could be anywhere in that huge dynamic range. So we'd better put in some kind of AGC, automatic gain control, and so let's get rid of that. That's not going to do the job. So let's look for that. Unfortunately there's one we designed earlier, we've pulled in, and what this does then is takes in some wide input value. In this case, where we've got 16 positions, it will take a 32-bit value in, and we can select to go to the output a 16-bit value from all the possible locations where you can pull 16 continuous bits, either from, if you imagine the 32 bits in a line, you can choose 16 bits of those either from the left hand side, the most significant bits, or slide along towards the middle or towards the right hand side. In fact actually 17 positions, but let's not quibble over that. We'll put 16, we'll use a select width of 4 to be able to address all those different positions. So we'll go OK. We'll actually Control C, Control V, have a second one, because we're going to need to do that to both the amplitudes. So again, clock comes from a sample clock. The clock enable we're going to make a constant. We don't have a constant to hand, so let's get another constant. this is a value of 1, bit width 1 to enable the 2, and this select is actually going to come from the volume control here, actually coming out of the 32-bit value, but we'll just take the lowest 4 bits. Okay, so let's concatenate these two 16-bit values. Concat. And okay, that should pick up the bit widths automatically. T-valid, that's going to come from this rate here. So if you remember, this is our 32 kilohertz signal. So we'll use that to clock the codec. Either of these would do, they're both at the same rate. And the clock, again, will be our sample clock. And if you remember, the output of the codec has the amplitude and phase concatenated together, so we better slice off the amplitude part, which is the lower 16 bits. So this time we will just use a simple slice. So we've got 32 bits coming in, and we want to take the lowest 16 bits. Data in, and the data comes out here. Now, so we have our local oscillator and this part here, which we can call our radio. So let's go ahead and call that our radio. These blocks here are going to constitute our radio. So create a hierarchy, and we'll call it radio. Okay, and there we go. Let's have a look at this, see what's going on. Now, this is actually our data out. Okie until we put local oscillators in it. Now, seems to have been this sneaky in here. This is the LEDs, which are currently being defined by that control block from the ARM chip, but let's not do that. Let's get rid of that, and get rid of that, and we'll actually drive the LEDs from the signal level detect. So let's take some bits from there. So we're going to slice 8 of those bits. We've already got the slice there, don't need that again. Let's get rid of that. But which bits we're going to use? In fact, let's choose a bit higher up in that range of bits, and it might scale to a usable range. So that set of 8 bits, so the 32 bits coming from the signal level, and we're going to drive the LEDs. Now that, let's call that LEDs. Okay, and this here is our amplitude signal. Now, because the amplitude is always positive, whereas if we're going to use this to drive a speaker, we really want just the AC component, so we better get rid of the average value here. So we need to do some kind of baseline subtract, get rid of the average value. So let's stick a bit of logic in here to do that. So what we'll do is put some subtract element, add a subtractor, come on, there we go. We'll make this a subtractor, and we don't need the clock enable. I'll just put this onto manual to make sure we get what we want. Signed 16-bit values, the output 16. It's not a constant input. We've got another input which is going to be 16-bit signed. Okay, so now we need to work out what the average level is to subtract, so we'll do the accumulator trick. And so what we'll do now is configure this. We're going to average over a large number. And it's manual signed 16-bit in, 32 out. It's now down manual 1 clock cycle latency. That's good. What else? So we will accumulate that value. We'll get rid of the bypass, we don't need that. We will take this accumulated value we're averaging, and again just look at the top 16 bits will be the average value. So slice, zoom in here, see what's going on. Takes 32-bit value in, and we're going to use the top 16 bits. Okey-dokey. And we're going to use those to subtract from our input, which we're taking from here. We are clocking from our same ADC clock, sample clock. Accumulator as well. Actually, on the accumulator, let's put a CE, because we're only getting new values at 32 kilohertz, so there's no point accumulating away at the full 125 megahertz. We only actually want it to accumulate when we've got a new value at the 32 kilohertz. So we pick up that 32 kilohertz from this T-valid signal here, if you remember, is coming from the mixer and low pass filter, so that's our 32 kilohertz signal. This, and this we're going to call in a sub-block baseline subtract. Okay. Where's it gone? Zoom out. There we go. But we do want an output from it, and the output comes from here. So create pin. Want it to be an output, so speaker out. Okay. From there. So let's close that for the moment. Have a look at how radio looks. So let's add this line subtract. Let's put a pin onto that. Another thing that would be good to have as an output is some kind of strobe signal which gives our 32 kilohertz update rate. That would be useful, and we'll pull that off T-valid. which is that one. Okay, we'll just check. Yep, that's our 32 kHz signal. Okay, park that again. Go up to the radio. Okay, and so that's our speaker. Yeah, just go back and have a look at that. Speaker signal is a 16-bit value. So if we're going to drive our DAC here, we'd better slice off 14 bits, so we'll get another slice. And we'll pull off from the input 16 bits the top 14 bits. Okay, so input from speaker out, output to the DAC. Okay, we've got another DAC output, so we might as well make use of it. So let's take a copy of, pull this out on screen. Let's pull out our demodulated signal, just would be useful for debugging. So for example, we've got it here, which is going into the signal level detect. If we create a pin, which will be an output, and we'll call it after mixer low pass filter. Okay, and we'll connect that, not directly to that, we'll connect it to a slice. So let's get another slice, because this is going to be a 32-bit value, and let's get the top 14 bits. So that we can send those to the DAC. That would be useful for debugging. Okay. System. So after mix LPF, 14 bits will send to the second DAC channel. Okay, so that's our radio. Let's tidy up. Now there's one more thing we can add, is to stream some data out from this process. We're making use of the fact that we put a FIFO on this bit of logic, so we can read this out from the ARM. We set up the drivers to be able to do that, and that'll be useful from a graphical application to be able to pull out data and display it to see what's going on. Now if you remember, we had this clock converter which takes data from the ADC clock domain and puts it into the ARM clock domain ready to go into the FIFO mount. So we're going to feed data into here. We don't see the data input. We need to click on here to see the input and zoom in. So we're going to feed in data here. We're going to take data from our radio module. I've not got anything maybe directly useful yet as an output, so let's create another output. Zoom in here. We might as well take two signals and concatenate them together into a 32-bit value and then stream out to the FIFO. So two values that will be of use would be that we've got a 16-bit value here, and going to the speaker, what do we have? That's a 16-bit value as well. Okay, so let's get rid of that. Command to assign again. Stick together
this value and the speaker value. So pick up a concat block, and take 16 bits from there and 16 bits from there, and this will make an output pin, and we'll call it data to stream. That's what we're going to stream into the ARM processor. Now you remember that this data is being updated at 32 kHz, so the other signal we need as well is this strobe signal, which is a 32 kHz timing signal. Okay, so go back up to here. This is data to stream. The auto width working out bit hasn't clocked onto the fact that this is a 32-bit value, but we can check that later. But it should be a 32-bit value when we send the data input. And the T-valid, we're going to use the strobe to clock that at 32 kHz. We're not going to bother reading T-ready, we assume that it's ready. Okay, so that looks good. Good as ever to save. And we're going to export that again. Well, just before exporting, one thing we should do, because our design is approaching completion, is run a validate to check that everything's okay. Oops. Right, so in one of the blocks, we're missing a clock, and that was in, so level detect, yes, one clock pulsar required a clock input, and we'd forgotten it. Okay, save again, and let's try validate again. Ah, yes, we've not put in a select to the AGC. I said we were going to do that, so that's in here. The AGC, that's here, yes. So let's put in a slice block, because you can remember we're going to take the lowest 4 bits of the volume. So we're going to have 32 bits in, we're going to take the lowest 4 bits and send them to the select input of our AGC block. So this slice, we're going to create an input pin called volume. Okay. Pump that again, and that volume comes from our configure block control, which is here. Cool. Let's save that again and validate. Okay, it's all good. So, I didn't say it's going to work, but at least it's logically consistent. So we will export that, the block design, as before, to our instrument, blockdesign.tcl, overwriting the one that we already had. Block design, instrument SDR, that's correct. And yes, really do want to do that. Okay, so that's pretty much it. We've now got a block design for a software-defined radio. So the next stage is to build this up into a full system. We've got the block design, all our designs encapsulated in this diagram here. This has all the logic, and we're going to wrap this up and plonk it into our Red Pitaya.
So to recap our design for a software-defined radio, a couple of tips that when we passed analog data in this radio design, sometimes we had unsigned values and sometimes signed. It's very important that the input to blocks is correctly specified, because if you treat unsigned as signed, then you're going to get some strange results, and your signal will be quite corrupted. There is still an error on the volume. We've inverted these values, so you need to subtract these the values going into the radio block here from 15, because 15 is actually the weakest volume and 0 is the loudest. So that will need to be inverted, but that can be simply done here. Go back to the system view. And so to recap the different elements of this design, so we have the Zynq block here, which represents the ARM processor connection to the ARM with its associated reset function, and an AXI interconnect, so that gives communication through this AXI highway, which allows streaming between the different blocks. So this block here is the ADC DAC interface, which allows us to receive data from the ADC, so in our case from the antenna feeding into the radio block, and then in demodulating that signal in the radio, we put an AM signal back onto this DAC line here, DAC1, and we've also added another signal into DAC2, which gives us some debugging capability. We can look, for example, on the oscilloscope at the signal that's going on here. But also we put in a facility to stream data digitally back into the ARM, so that was this line here. If we zoom in, we took data from this radio block and streamed it into this block here, and we clocked it with this value here, that each time the value was updated we sent a 1 clock cycle pulse here. So in fact you can send any data you like, provided you clock this correctly. And then this goes on into this FIFO block here, so that it's buffered up, ready to be read out by the ARM.
In the next video, we'll run the make file to compile the design ready to go onto the Red Pitaya board.